Well, hey everybody, thanks for coming. So I'm Niels, and at KPMG we're in a group called the Data and Analytics Lighthouse, and we essentially do a lot of data and analytics consulting for many large companies. But today I'm going to talk about a problem that me and one of my former colleagues looked into, and also another Kishori who's here, and also Guohao, where we worked to try and come up with an explaining model of the recommender engine that's found in Spark. So without further ado, we'll get to it. So just as sort of like high level, it's a bit of an understatement to say that recommender engines have supercharged online retail. And they're pretty essential in terms of like marketing and online experience and personalization just in general. And in fact, the models themselves have been shown to be highly influential over time with what people consume. Pretty famously, in terms of Netflix and YouTube, they communicate that basically these are the primary way that customers access their content. Recommender engines are pretty essential for this personalization effort that many of these firms want for their web experiences. But I'm here to tell you that what they should probably be explainable. So there seems to be a growing concern that these models are black boxes, and customers are generally kind of aware that their recommendations are somewhat related to their browsing history and their profiles. But in the era of GDPR, there might be, at least the wording is there, that there's going to be a call for increased accountability and transparency of models. So we're, now the new goal is basically we should be striving for models that are both effective and understandable. So, but in this talk, we're going to really talk about basically a method that's in spark.ml, or proposal method for spark.ml that explains recommendations for the popular ALS recommender model that I'm sure many of you are familiar with. Just as sort of a high level, we're still introducing systems, but basically there's sort of two ways to go about developing a recommender system. One is collaborative filtering, and these models use the interactions between users and products to develop general trends in the data. And then basically you can recommend along these general trends. So it's like you're starting to look like somebody who consumes these sort of things. And that sort of rationality is what drives collaborative filtering. The other kind of model is called content-based filtering. And content-based filtering recommends products that are similar to the product that you're currently looking at. So you can go to a product description page, and basically you'll say, these are products that are similar to you. And so these are based on properties of the products or profiles of the products. And the first problem, the collaborative filtering problem, basically you have to find those relationships in the data. So you have this cold start problem, which basically means you can't recommend to anybody without learning these data. And then if you have a new person that comes into the model, in most cases that you need to fit the model, and then you can recommend to them. And in the other case, you don't have that problem, but you're basically left with sort of a more unsophisticated model. You're left with a model that can only recommend based on sort of where you're starting at, and also the features of the product. So you have to build up that profile of the features that are relevant that people want to recommend to. And in the sort of collaborative filtering pace, you kind of get that by default. It learns those sort of features. So because you can sort of get the best of both worlds, you have people who do these hybrid recommender systems, which are increasingly complicated, and you'll find that that's sort of the case in the back end of many recommender systems. Is like there's some combination of the two approaches. So talking specifically about matrix-based collaborative filtering, it's probably the most widely used recommender model. And what it tries to do is you set up your users and the items that they've looked at in this user product matrix. And then the model tries to decompose this into a number of implicit latent factors. And the implicit latent factors are basically these dimensions of high correlation in the data set that sort of people tend to consume products along. So maybe like action movies versus drama movies might be one that's seen in like in music data set, or in the Netflix data sets. Or different genres of music are also found along these lines. But it learns it sort of what people consume. And it wasn't the entire component of the model that won the Netflix prize, but it was a very, very large component of the model that did win the Netflix prize in 2009. So it's quite famous, and it's also implemented in spark.ml and MLlib. It's known to return relevant recommendations, and it's a major part of many recommendation systems out there today. And in fact, this implementation is very, very popular because it scales. And on the right here, you can sort of see how you got this data matrix that's being decomposed into two factors. The X is known as the user factors, and the Y is known as the item factors. And if you basically, those are where your data sits along those implicit factors. Your users and your items fit along those implicit factors. And you can estimate any given value in that matrix by doing the inner product of those two. And so that, at a high level, is what this model is trying to accomplish. In matrix terms, this is the singular value decomposition. For people who have fit this model, you know that you have to choose a rank, which is the number of latent factors to fit. You need to choose a lambda, or the regulation parameter, which is like this thing is fit by basically performing least squares iteratively back and forth between the matrices. And you got to choose a regularization parameter to make it fit a little bit better. You'll have an alpha parameter, which is basically the confidence. It's a confidence parameter, but what it basically means is that this is the weight of the data that's going into this decomposition. So like a high alpha parameter means that basically it scales up all the events that you have in your original data matrix. So those will have very high, powerful influence on the data. It will almost be like a pure event data driven distribution. So, and then probably the most important thing that you have to decide when you're setting this up is basically, are you in the explicit model or the implicit model situation? And basically this corresponds to whether your users are rating something, which is basically a continuous value between a lower and an upper number, or are you inferring someone's interest in an item based on item clicks, adding them to cart, purchasing things? You can sort of add up, come up with a complicated weighting system to figure out what that interest is, but you're learning it implicitly from their actions. So you'll find that these are really, really different models, and basically the very first thing you need to decide is which one you're in, because they actually are quite different, and you'll find that one will give you very, very poor performance unless you do it that way. So that's sort of, in a nutshell, matrix-based collaborative filtering. One thing that's overlooked, though, is that these implicit latent factors give you a ton of information about how people consume things. And so the outer product of the user factors and the item factors gives you this similarity matrix, which basically is a distance. And so you can start, these things are really useful in their own rights, because you can basically start clustering them, and then users that are consume items together are close together, and items that are consumed close together are close together. And so now you can start basically think of things like using this for different kinds of outreach or advertising initiatives, or learning about your product line in a way that you didn't really understand. So there's a lot of exploration that you could do here. But I'm going to take it a step further, and I'm going to say that we can come up with a user-specific perspective on the item space. And what I mean by that is basically we're going to adjust this item space so that it's custom to the user's opinion about items. And the way we're going to do that is we're going to basically do some linear algebra, which I know is fun for everybody. But what you can do is basically you're going to adjust those latent factors by this weighting matrix W. And how do you come up with W? Basically, you take the inner product of your item factors, and you adjust this inner product by the consumption pattern of a particular user. And that gets you, and then you invert that matrix, and you get the weighting matrix of this space, which is going to twist those latent factors in a way that's custom to this user. And so when you do that, and you do the outer product between those two things, with this weighted factor, you're going to get a user-specific item-item similarity. And so that's kind of abstract. So let's take an example. So let's say you had two different kinds of two people. One's a runner, one's a musician. And the runner's interested in shoes, and the musician's interested in musical instruments. So you can see in the original item space on the right there that there's some structure that exists. So like shoes are close together and maybe the musical instruments are close together. But in the user-specific cases, the runner knows more about the differences of the items in the shoe because they have more opinion about it, and knows less about the musical instruments. And then vice versa for the musician. The musician knows a lot more about musical instruments than it knows about running. So just like to show that visually a bit. So here's our original item space. And the shoes are close together, and the musical instruments are close together. And this is Y transpose. This is the outer product. So we're going to scale that by this adjustment to the implicit factors. And what this is going to do for the runner is going to spread those out and collapse those in. This is sort of a hokey example, but this sort of gets you the point of what I mean by a custom user-specific item space. And so, yeah? Yes, for every user. Oh, the question was, do I create an item matrix for every user? And I do, yes. Yeah, it's specific to the user. Now, our musician, on the other hand, it's same setup, weighting, transpose, and this might be where it ends up. And so this is the final space for the musician. So why should you care? So the user-specific item spaces allow us to decompose recommendations into their original component parts. So it turns out, like this decomposition is exactly the way that you get the recommendation score in the current ALS algorithm. So this is exactly what it is. So what it does is that you can take your custom item space, and then you can say, these are the blue items here are things that this user has consumed. So you had 2 shoes and a set of drums. And essentially, you can weight how far away, so we're trying to figure out what this user's opinion is about this item. So, well, it's the weight of what they consumed it with how far it is away from that item. Similarly, we can say their opinion about this musical instrument over here is this decomposition as well. And if we run the numbers, you'll find that this one person is more of a runner than they are a musician, so the runner has a higher score, but it was also closer to these things in the item space. On the other hand, the music product is closer to the drums, but the other two still had an impact, albeit kind of smaller. And so this is a bit of a contrived example, but you can see how you can get the absolute decomposition of the scores into what the user consumed. So this is pretty interesting, because now you can say, well, you got this recommendation because you clicked on this, and then you bought this, and then you added this to cart, and it basically, because of this consumption pattern, and sort of combined with our perspective on how people view these items, put together explains what this recommender was doing for you. So how could you potentially use this? Like, I mean, well, you can come up with some reports and basically say to the user, like, well, you're getting a recommendation of this, and it's coming, so much percentage from this, and so much percentage from this, and so much percentage of this, and the absolute value of those two. So you can start giving reports to somebody if they wanted to know. And the absolute values also tell us that which items over multiple products have an undue influence on your recommendations over your entire item set. So that could be a problem for you. Maybe maybe socks, for instance, because everybody buys them, has an undue influence on everybody's products. So it might not be something that you want or something you first want to know about, and then maybe something you want to do something about. It also, because now that you can look at a recommendation and see its decomposition and where the weight is coming from, you can also sort of get an intuition about what kind of things the CF model is learning, although you could have probably done that from the original implicit factors as well. But in this case, it's around a specific recommendation. One other thing that you could do is if you had a particular set, like a prior set of information that you wanted to change the scaling by, like you could say, a certain set of items are on sale, I would like them to be lifted up in the kinds of recommendations that we're levying. Or there might be some things that you don't necessarily want to, or there's the one that's like basically drowning out all the influence of everybody else's recommendations. So these are sort of things where you can start doing what are called man in the middle, where now you can you could ask users if you think this is a relevant thing, and they could upweight or downweight. Or internally, you could say, maybe either understand what the recommendation is doing or upweight and downweight some of these item contributions in any way you like. So, so getting it done, fortunately, like alternating least squares model in spark.ml reports these item factors. So you can just take it directly from the model. And there's a number of tricks to getting it done on a large number of data, which we've done for you. And we're proposing this as a change to ML. And, but what you need is basically you need the item factor matrix from the ALS model. You need the original user product ratings, because you need to take those factors and you got to scale them up and down for every user. And then you got to bring in those regularization parameters that you hyperparameter tuned for that model, because those are also in the equations all over the place, so you need to use them as well. And then on the right, basically, this is just a very simple way of doing it. You load your ratings, you fit your ALS model, you pull out the item factors, and then you pass it into our new class, ALS explain, and you bring in the item factors, the rating, and the regularization parameters. So we've used it on the movie lens data set. It's very famous. Basically, if you're doing a recommender model and you don't use the movie lens data set to check, it's really behooves you to do so, because it's a very popular model to do it. And it's not terribly large, but it's sort of, people know what to expect. And so here are some explanations for a particular user about particular movies that they might be interested in. So in here, for Home Alone, it seems that people who watch Home Alone tend to also watch Star Wars. So those are highly weighted in terms of like the behavior that you did in the past that really recommended Home Alone for you. And you'll notice that most of these movies are either adventure or funny, so that makes sense. And then Fight Club, which is a rather intense movie, has a bunch of intense movies from your activity that basically added up to you getting recommended Fight Club. And the other thing that we can tell from these two plots is basically this person likes, or the model thinks that he likes Fight Club more than he likes Home Alone, because basically the mass on the right-hand side is quite a bit more than the mass on the left-hand side, because these are absolute values, although you could change them to relative values and then they would be percent as well. So we're going to talk about next steps, and then I'll show you another demo. So currently, when we do this in ALS explains to the question up here, do we calculate every item matrix for every user? We don't. We calculate just only the values with which they've touched, because there's actually, items by items is a large matrix to respond to everybody. So, but it's a legitimate thing to ask for. It's like, give me this person's item similarity matrix. I'm very, very interested in it. So that's something that we could add. It's just we haven't done it yet. Also, there's performance improvements that could be in this. Like definitely, there's some. We did quite a bit of sparse matrix in implementing this, but we could do a bit more. And also, there's approximations to the inverse that we could also add to this as well. Those are sort of the two major steps. One is doing the arithmetic, and the other one's doing the inverse. The inverse is, well, it's still important because your factors could be large, but in some cases of applying this model, you don't actually need a whole ton of factors. So this is also one of our first proposed changes to spark.ml. So it's our best guess at what is supposed to go in there. But we'll work with the community there. So anybody who wants to come talk to us about it later, we're all ears. And finally, this is an interesting find because the ALS paper is 10 years old, or at least 10 years old. And yet this method really wasn't implemented in Spark. So if you go back to the Walensky paper, which I've been referencing which has been on the slides throughout, that was the original description of the implicit ALS matrix that everybody's talking about. You just read it in the back, it describes this. This is what it should do. And I was like, well, this should be in Spark. Because now that people want to explain it, it probably should be done. So that's all we really did. But that being said, we want to basically take our energy and put this towards sort of other more sophisticated recommender models that are being used. So autoencoders and feed-forward deep neural nets, but I'm sure, I think the last talk did discuss that quite a bit. So now, in terms of a quick little demo of it being worked on sort of a contrived data set, so here we go. So here you go. Basically, the only difference that you have to do is basically you have to load in our explain class. And then I've generated some rather contrived example here about recommendations. So it looks like standard ratings. Let's say that they're click counts. I've generated 2 distributions, one for musicians and one for runners. Go figure. So basically, this is the probability distribution of the clicks of the musician, and you see that it's highly slanted towards the musical instruments. We'll notice that the musical instruments are the small numbers, and the runners are the larger numbers. And in the middle, I have this phone that we'll see that they're both kind of interested in the phone. The runners, on the other hand, are interested in the shoes, and somewhat interested in the phone as well. So we've generated a 100 user sample from the above, and here's a histogram of what was generated. So it's a probability distribution, so it's not exactly. But because you do that, you can also see sort of this is the correlation structure of the items that people tend to consume together. So we found that basically there's a group for shoes, and predictably there's a group for musical instruments as well. And then we find that this phone in the middle doesn't really know where to fit. It doesn't sort of in between the 2 clusters. Dendrograms put it somewhere, but it didn't necessarily have to be there. So next you'll run the ALS model. So you start your Spark session if you still have to do that. If you're in the Databricks environment, of course you don't have to do that. Then prepare some ratings, and then feed in your data frame to ALS, and then fit it. So now here with ALS explain, basically you pull from the model the item factors and the ratings, and then because it's Python, you need to specify which columns you're using for user items and ratings. And then you have a regularization parameter, alpha, and then we have this optional parameter, which is top explanation, which basically says, stop after the first 10 items. This is just to limit the size of the recommendation scores that come out. It's a hierarchical data structure. We might think about changing this to just being the table in the code, but we do this to sort of save space. But in any case, since it's helpful, this is finally what you get out. So what this is saying is basically for user 100 and his recommendation on item 1, his overall score was 1.00 something. And then the product contribution from product 3 had a 0.47 contribution to that. And then this is expressed as a percentage over all of them. And so from here, that's where we get our influence scores. So we can do a bit of exploratory analysis. So we can look at user 100, who I know isn't a musician because I generated the data set. We'll look at his explained, the explained idea is 1. And then we'll take a look at the plot. And what we notice from this is that basically it's explaining one of these musical instruments, and we find that all the explanation weight comes from musical instruments, which is what we hope. Again, now let's find his recommendation for item 9, and you say even though he looked at a ton of musical instruments, these things don't explain where the recommendation is coming from in this case. In this case, it's because he looked at that phone, and then he also, kind of looked at one, shoe. And so basically this is saying all the influence from this recommendation are coming from those two things. Yes? You might hold the end? Yeah, okay. Again, we can do this for a runner. So now I choose a runner and say, let's explain a shoe. And basically this would be the distribution. And that, mainly influenced by the other shoes and the phone. If I look at a musical instrument, now all the weight comes from this phone, and not very much comes from the shoes. And then if I do the interesting thing, which you're probably all wondering about, like what happens if you recommend them the phone? Well, since the phone is kind of on both sides of the equation, we got a kind of a flat distribution. And that's sort of what we'd expect as well. So sort of in summary, this is sort of the method, and we're proposing it for spark.ml. Definitely want anybody who's got experience submitting to ML to come talk to us about what this code should look like. But this could be a pretty relevant piece of extra information that you could provide for your recommender models going forward. And fortunately, we've got a lot of time for questions, so please let me have it.
Check. Thanks, Niels. Just one request I have, that if you have your Spark AI Summit app on your iPhone or Android app, Android phones, please do rate this talk so that it will help us to make it even better. So, and with that, there'll be 2 mics on these aisles, and if you have any questions, please line up behind those lines. Thank you.
Yeah. Okay. So I had 2 questions. The first one was regarding the plot that you showed there. So basically, from what I understood is that you're generating a new matrix, item matrix of only for the specific user and for the items that they have seen. And the plot looked different for a different item. Like you were trying to explain how for the phone it looked a little different in the demo. I was trying to understand how that matrix changed with an item change.
So the score is made up of 2 components. One is where the item ends up in the item space, and one is the consumption factor. So it's a bit of a two-pronged problem. One is either the item ended up close to that item where it was in the space, and that the similarity is dominating, or this person just so happened to consume an item a lot. And so either one or the other, if you have a high score, it's either because that item was close to the recommended item in the item space, or the consumption happened quite a bit. So one of the 2.
So basically you can answer 2 things. One thing is that this person generally looks at musical instruments, so that's why I recommended this other musical instrument. But the other explanation that you gave there is this person looked at this specific phone, and for that phone page, I'm recommending other phones, let's say, because of, you can answer the second thing as well? Basically, the explanations change based on the item itself is the question here.
It's because, yes, so basically the phone either exists in between the 2, and you can't have a very strong opinion. Basically, when you don't have a very, very strong opinion about it, all that's either left is the signal or your consumption or your behavior. So in the absence of behavior, you have similarity, and with behavior, you have a combination of the 2.
Makes sense. Yeah. And the second question was how well does this perform, especially in cold start situations? Like I've seen sometimes Netflix explaining why they showed me this recommendation. Sometimes it doesn't make sense at all. So in case of cold start, what are the results looking like?
That was a good question. So this is definitely not one of those friendly to the cold start situation because it's you have to fit them in ALS. So basically, if you can't fit an ALS model, you're not going to be able to explain it. So it still has that cold start problem. So, but like you said, you compare it with you know, an item similarity version that's based on profile information versus collaborative filtering methods. Yeah.
Thank you.
Thank you. All right.
My question is kind of related to the cold start problem, but
Yes.
just with the demo you just did, it looks like for certain cases, the influence score seems pretty explanatory. Sometimes it just seems random, or just it doesn't really have a lot of information in it. Is there a way to say, give some kind of confidence or whatever thing to the recommender to say, I know what I'm recommending is probably making a lot of sense, or say, I'm just guessing?
I think that's one thing you can say is basically, first up, how strong was your ALS fit in the first place? Because if you don't have a strong ALS fit, then basically everything's out because your implicit factors are out. The next question would be basically, is this recommendation having a strong contribution from basically either S or C here, right? And so that's one other thing that we can add to the, right now the influence score is both of those multiplied, but we could split them out. And so basically we could say, this is based purely on similarity of items, based on the bulk group of people, based on collaborative filtering, or we can say it's from both the similarity and the fact that you clicked on it 100 times might also, so basically you can sort of say, you know, how much weight did you put to this? But in terms of like the ground truth on where this explanation is coming from, then it's sort of out to, up to some interpretation at that point. So because we're still sort of exploring, one way maybe to be like to take those statistical distributions and figure out whether our explanation meets the statistical ground truth. But I don't think that's necessarily what the relationship is. I don't think it's just this is the probability that people will select it because it's also got the correlation in there as well. So, but a good question.
Thanks for the talk. It's really great. So I have a question about so you basically decompose the recommendation into the history of that person's purchase or interest, right? But I'm just wondering, because we are doing a collaborative filtering, like I'm assuming like other people's behavior actually also contribute to this decomposition, right?
Correct.
So can we capture that, or we don't?
Yeah. So it might be like we might express how much, you know, this moved. This by itself is just basically everybody's opinion about items in terms of based on the behavior. Right. But we might say how much your opinion differs from everybody else's opinion by coming up with a distance that describes this. So that's a good idea. all great ideas, but I think the problem's sort of like underserved a bit. So,
okay,
yeah.
Thanks.
I had a question on how you would evaluate such techniques like explainability techniques. Like, is it just looking at the data as a human, or do you have any mechanisms to do so? Because let's say you have this now and you come up with an improvement over this technique to like provide a better explanation.
Right.
How would you evaluate that?
Yeah, it's a good question, similar to the other question.
Yeah.
Basically, yeah, we should explore sort of like if there is some mechanistic way that is driving people towards these correlations of consumption. It's sort of like we need to come up with a measure of how better they are. So I'm all ears for opening that discussion and thinking about it. But these are good questions. Evaluating this method is you know, aside from holistic looking at it, we're still thinking about a measure that would capture that kind of intuitability. Yeah.
And also, what approaches are you looking at for exploring explainability for models that include like autoencoders and things like that?
Yeah, that's really interesting. So we're exploring a number of ideas. Basically, this one had the nice feature of being able to be decomposed as a linear combination.
Yeah.
We might also expose basically taking like autoencoders and feed-forward neural nets and also figuring out if there's a linear combination, like a weight that we could come at that we can decompose back into the original data space. So like, we seem to be able to explain something if it goes back into the original behavior of the data. Like that's a powerful sort of statement, as opposed to being like in let's say like looking at the factors themselves. It can be quite confusing because they're all twisted by a linear combination. And it gets even worse with like the feed-forward neural net when you're looking at the third internal layer, where it's like, well, it went through like basically 3 logistic regressions, and then this is what we end up at the third node.
Right.
So 3 nonlinear transformations can be a little bit hard to explain. But yeah, we're kind of exploring if we can do some algebra and come up with a linear decomposition of those other models.
Right. Thank you.
Hey.
Like, how would you deal with like changing tastes? So let's say your musician decides to take up running, and so now he starts going and looking at shoes, and maybe he wants he cares more about shoes now than he did instruments.
Yes.
Is it just like adjusting the alpha or weighting recent data higher?
I think we could start looking at, in terms of changing it from one side to the other. So basically, you could look at these factors internally as someone who's making the model, or externally as a person who's consuming the model. You might ask the users to basically say, here's your decomposition, like, click on this to see if you think that this was a helpful decomposition. It was like, was this a helpful do you think that this decomposition is correct for you? And now you can start crowdsourcing the model back to yourself. But now you're like opening, I mean, I think YouTube does this, although it's like, was this what you expected? Why did you receive this recommendation? Those are starting to happen. And then on internal side, you can sort of look at your product catalog and then look at this overall and say, how much variation is each item contributing to my recommendations? And then you can do with what you will. You can change that prior. You're like, maybe the prior should be flat, or maybe the prior should be biased towards things that are on sale, or maybe the prior should be biased to expensive items, or something like that. But I'm not sure if I totally answered your question. It was a little quiet.
Kind of. Like, I'm just thinking about my daughter, for example, like when she watches YouTube.
Yeah.
Like, she has changing taste. She'll go from Pete the Cat to more advanced videos, and there's a progression over time.
Yeah.
And so sometimes she'll get a recommendation for something that she no longer cares about.
I see, yeah. So there's sort of like when you fit these models, you basically are always being careful about what the look back period is on those. So you can, the simple way that people usually do that is like, we might have a window for like a week, like 2 weeks, multiple weeks, and then you can do a hybridized version of this. And then basically the hope is that something relevant will come up. But there's also the question of modeling time explicitly in this model. And we're also thinking about how to do that. Maybe there's sort of like a Bayesian conjugate prior that you could do over time to basically, you just pass the parameters forward, and then basically, I mean, it's also good because you don't have to always fit the model over and over again with that. But yeah, that's definitely something that you could improve. And then you could do explainability over time if you have the same decomposition, which would be even more interesting. So thank you. And I think we're at time. Thank you.